Okay, so let's do some equations with chemostats. You can think of a chemostat as kind of like a CSCR reactor, but it's more used for the biological equations. So I can draw out a little sketch. And what happens is we want to convert substrate to product. But the thing is, we use this empirical stoichiometric coefficient that we call like the yield factor, which is just the amount of S that gets converted into X. And then it's X. It's because these biological reactions, it's not like saying, oh, like two water molecules form this oxygen, and like these things ends up being really complicated. So you can think of the stoichiometric coefficient as like an empirical stoichiometric coefficient. Like empirical, I mean, you'd have to do it in the lab, and then you see what the result is, and it ends up being like a really messy decimal. It's because it's just lumped. You don't know what the elementary reactions to this biological reaction actually is. But anyways, we have a chemostat, and you can think of it as a reactor that helps do this process, converts the substrate S into the product cells that we call X. And we call the output S and X. Input is S naught, and X equals 0 for this case. KD is what we call cell maintenance. We're going to be ignoring it for this video just to draw some very simple calculations. It's because when you make these biological cells X, a portion of the energy will be used to just maintain the cells, and it's not actually going towards any of the reactions. But when you do that, the models become a little bit more complicated. It's nothing too bad, but for this example, that biological coefficient is 0, and also the inlet X. And I know it's kind of silly. It doesn't really make sense except for very few applications to be putting X in the inlet because of Le Chatelier's principle, where, you know, if you're putting product into your reactor inlet, like, it's going to be like you're going to make less product. But some cases it's viable. In this case, it's it just depends what you're dealing with. But for now, we're going to say X not equals 0. But of course we're going to need substrate to convert, so of course we're going to have that in the inlet. And then we have a constant volume phi, and the F, there's the flow rates in and out. dV dt is 0 because the reactor has constant volume. It's simple. So I say that this is for the Monod reaction, so we can write that out. And it's, you know, it's not the same as the Michaelis-Menten, don't confuse it. In this case, we have the maximum gross product. That we have the substrates, we have the constant, and this is the gross specific rate. And what we can actually do is we can write mass balances for everything. So we have the two chemicals S and X. What you can do is, you can do in minus out, plus or minus reaction equals accumulation. But accumulation equals 0 since this is kind of like a CSCR. And let's do it for X. And what we usually do is we usually put it in terms of moles per liter, and to do that we multiply the feed. The feed is like volumetric flow rate, and we multiply it by X, which is concentration, and by multiplying that you get moles per liter. And then for the reaction, what we can do is, remember this reaction? We know that we're going to be gaining X, so we say U net. And here we have to recognize that this gross specific rate equals net plus KD. If there is no cell maintenance, then the gross specific rate is just the net specific rate. And then you can use U net synonymously with this. But for the X, it's net, because we're going to be subtracting that KD from it, but in this case KD is 0. And you multiply it by XV. Okay, and then we can work with that. And you'll see actually that the x's cancel out. And you can move that one to the other side. And F over V is actually what we call D, dilution rate for the chemostat. So this works out. And also this, since we said before, U net equals that UG. So that's good. So you remember the Menotti equation? I wrote it above, but I'm going to write it again. And accidentally messed that one up. Okay, good. And then what we can actually do is just rewrite this in terms of D. So substitute D into UG, and we need to isolate for S. Okay, good. And then we solve. And this is the way we usually write it. Okay. Good. And also we can write the other balance in terms of the substrate. Now be careful with this one. So the inlet and outlet, and now we're using up the substrate, so you have a negative sign. And now we have UG is the gross specific rate. In this case, since KD is 0, it doesn't really matter, like UG, U net. But if you do have KD, cell maintenance, then you have to kind of be careful with this. So I'm going to speak generally, and I'm going to simplify it down. And it's multiplied by XV. Now be careful, this is an extra thing. You have to divide by that stoichiometric coefficient. See? All the way from above, this empirical stoichiometric coefficient we called the yield factor. And now you have that reaction part, and that's just equal 0. So now what you can actually do is you can divide by V, and remember that F over V is just D. Let's make that look a bit prettier. Okay. And we said before UG is just U net as well, equals D. Well, and you can cross out that D's because they're on both sides, so UG is just D. So it's very easy in this case. Okay, so that's the yield factor on the other side, equals X. Okay. Haha. So now we have equation. So this all turns into algebra because the chemostat is like a CSTR. Like you don't actually have accumulation, so you can actually reduce the equations to algebraic formulas. And when you actually solve the formulas, you can get profiles for the X and S, and you can get it very easily. It's not like a batch system where everything is like differential equations. No, now it turns into algebraic equations here. So we got equations for S, and we have an equation for X. And then we can even take it another step further if you want, since the equations are not so messy. And also, if you look at this kind of from a different viewpoint, you'll see that, oh, the amount of X you make is just a stoichiometric ratio multiplied by the reactant difference, and that makes sense logically. Okay. Okay, good. So now everything is set. We did it. S equals KSD over UM. So KS, UM, they're just constants. D is like a dilution rate, F over V, and you can just change either the volume of the tank, or you can change the flow rates on both sides. And with this one, yeah, everything else is just constants. So now, you know, D is like the parameter independent variable that we'd actually be changing. And now we have formulas for S and X. And for this one, so this is basically a chemostat with a Monod equation, where the feed of X naught is 0 and KD equals 0. It's very easy to solve. After this, I'll be covering some more difficult situations, such as like, oh, what if X naught is not 0? What if KD is not 0? Okay, hope you enjoyed the video.